Okay, in this problem, it's real similar to the last one. We're still considering calcium hydroxide and its dissolution. But instead of dissolving this stuff in deionized water, we're going to dissolve it in a different solvent now. We're going to dissolve it in a solvent which consists of 0.1 mole per liter calcium nitrate. That's actually really important because calcium nitrate contains an ion that is common to the equilibrium of the calcium hydroxide. Of course, that ion is going to be calcium. So we're adding calcium from a different source, a secondary source. It turns out that the equilibrium involving the calcium hydroxide dissolving doesn't care where the calcium comes from, but if it's present, it can influence the equilibrium. So we start where we always start. We write our reaction for our equilibrium. Calcium hydroxide solid dissolving to make calcium 2 plus and 2 copies of hydroxide. We also can start by writing our Rice table. Don't care about the solid because it doesn't appear in the equilibrium constant expression, but these other ions will because they're aqueous ions. So we need to start with writing initial concentrations for both of these. So here's the thing. Because we have calcium in our solvent, we have to consider that. And when calcium nitrate, a strong electrolyte, dissolves in this solution, it produces 0.1 mole per liter of calcium ion, and also 0.2 mole per liter nitrate ion, by virtue of that too. But the thing is, this particular equilibrium really only cares about calcium. So we put 0.1 mole per liter as our initial concentration of that ion, and we'll add a big fat 0 for our hydroxide. Now, the equilibrium will shift right because this is 0, so I'm going to make some of that. Oops, I made a mistake, didn't I? I'm not going to make x, I'm going to make 2x. And then once equilibrium is established, I'll make 2x of that. That's what I'll have. Likewise, I'll get a little bit extra calcium. I'll get x quantity of calcium. So at equilibrium, I'll have x molar calcium and 2x molar hydroxide. But the thing is, didn't I forget to write that 0.1 again? I did. The total equilibrium concentration is this, what we start with, plus our x. So in truth, I'm going to have x plus 0.1. This 0.1 coming from our external source of calcium, our common ion. So now what we do, go to our KSP expression. Calcium ion times the hydroxide ion concentration squared once equilibrium is reached. And we know that that's equal to 6.5 times 10 to the minus 6 because that's our value for this sparingly soluble salt. We then go in and plug in numbers. 2x was our equilibrium estimate of what the hydroxide concentration should be. Still have to square that. And 0.1 plus x was my estimate for my equilibrium concentration of my calcium ion. Of course, all that's still equal to 6.5 times 10 to the minus 6, my KSP. None of that's changed. I mean, it's very familiar to what we've seen so far, isn't it? Okay? So what I think we'd be able to do here is probably make an assumption that 0.1 is very big compared to this x. And if we did so, we just kind of get rid of that x term. Then we would have what? 4x squared multiplied times 0.1. I think that would be what? 0.4x squared equals 6.5 times 10 to the minus 6. And then all we need to do to solve for x is take the square root of 6.5 times 10 to the minus 6 divided by 0.4. And if we break out a calculator, four times 10 to the minus 3 is what I believe that I got for my x here. So what does that x mean then? Well, if we look back to our Rice table, it'll tell us. If we add that value to 0.1, we get the total amount of calcium present. If we take that number, multiply it by 2, that gives us the equal expected concentration of hydroxide in this particular mixture. So what does this problem really ask us about then? If we look back, it tells us we're dissolving the stuff in the calcium nitrate. We want to know what is the molar solubility, right? So that's what that problem's asking us. So what do we think about that? Is that equal to x or not? Because remember, this number 0.04 is equal to x. I'd argue that it is equal to x because look, one calcium hydroxide dissolves and we make one calcium ion. It's a 1-to-1 ratio. So x is the amount that we got from the dissolution of the stuff. So surely that 0.004 is indeed our molar solubility. All right, and it's easy as that.